Hi there everyone, welcome to the next Chem Complete episode in the Chemical Kinetics series, and today we are going to take a look at a lecture on chemical kinetics and activation energy. So when we talk about chemical kinetics and activation energy, you need to understand what activation energy is. An activation energy is the amount of energy required to bring a compound or a set of reactants to what's called a transition state. And when you head to a transition state, the transition state is the highest energy state where bonds are partly broken and partly formed in your reaction. So transition states require a certain amount of energy to get to that point because they're such high energy candidates. And the energy of activation is the energy at the ground state for your reactants up to that transition state. So we're going to take a look at two different representations here. The first one is going to be for a more spontaneous type reaction, okay? And the second one is going to be for a more likely to be a non-spontaneous reaction, so something that looks along the lines of this. Okay, now why do I say that? Because if we're taking a look at the axis here, this is energy. Okay, and if we look down here, this is something that's known as the reaction coordinates. So the way that you can view that is it's a timeline of the reaction as it's taking place. So we're basically following the reaction along as it goes along. Okay, now what you'll notice is in the case where it's most likely going to be spontaneous, we've got a energy level right here for the reactants, which I'll label with R, and right here for the products, which I'll label with P. So if you take a look at this, the energy that exists in the products as they're sitting there at their ground state is less than the energy in the reactants, and that's beneficial from a stability standpoint. So whenever you have compounds that are very high in energy, they tend not to be stable. So if you have reactants that are high energy and they can come together and produce products that are lower in energy, that's going to be a favorable reaction. And the opposite tends to be true when you're trying to look at non-spontaneous, or at least a suggested non-spontaneous reaction. And in a case like that, you're going to end up having these reactants that have relatively decent ground state energy, but when they come together or are forced together, the products that result are going to have a higher energy that are sitting there in the product state. So when you consider that, that's going to be a big change in activation energy. So the activation energy is the energy from the reactants to the transition state, which is the highest energy point. So that right there would be the activation energy. And here you can see it's going to be a lot larger for the non-spontaneous because I have a larger hill to climb to get to the transition state here. Okay, so that's going to be the activation energy, which we represent as EA. And you might hear this called the energy of activation. Obviously, it's the same thing there. All right, so how do we calculate this in relation to chemical kinetics? So the formula that we can use, it's known as the Arrhenius Equation, and it is your rate constant equal to, now this can get confusing, it's a large A, but this is not the same A that represents a generic concentration like we looked at in a previous lecture for the graphing of concentration and time. This is actually, this A is known as the collision frequency factor, and that's going to be unique again for each individual chemical setup that we've got. Okay, and then it's going to be natural E, and that will be raised to the negative energy of activation over RT. Okay, so this is the Arrhenius equation. And the Arrhenius equation, we want to just rearrange it here for a moment. And keep in mind that this R is the constant for the joules with gases. So we're talking about 8.314 joules per Kelvin mole. All right, so that's our constant there. And again, A is going to be what's known in this case as a collision frequency factor. In other words, how often are these molecules going to collide or come into contact with one another, because that will obviously be important in predicting the amount of energy required. If molecules are colliding more frequently in a certain setup, then the energy may not be as great as far as what's required there. So we need to see how often they're going to be colliding. Okay, now, we can rearrange this, okay, and get rid of that natural E by taking the ln of k. So take the natural log of the rate constant and set that equal to the natural log of the collision frequency minus the energy of activation, okay, over RT. So this has become simpler. And in a case like this, we can also rearrange it or sort of separate it out even further in order to make it graphically relevant, meaning we can then turn around and put it on a graph for a slope equation. And so we're going to rearrange it one more time so that we get the ln of the rate constant equal to, and what we'll do is we'll bring out negative energy of activation over R by itself. So if I'm going to factor that out by itself, that leaves the t in the denominator, so that's 1 over t. So what I did there was I just took this chunk right here and I separated it out into two different expressions, because one of them I'm going to use as the x on my graph. And then this ln of a, which was originally over here, I can turn around and move that. It is positive, so I'd put plus ln of the collision frequency. Now, if I take a look here, I have a y equals mx plus intercept. Okay, so the slope, if you were to graph this out, you can graph the natural logarithm of the k against 1 over temperature. And when you do that, you will end up with your EA over R as the slope. Now again, because this is negative, you're going to see a negative type of slope that's appearing in these types of reactions. So when we do that, let me delete what's down there. Okay, so when we do that, let's go ahead and draw this out. Okay, we're going to have ln of k, and we're going to have 1 over T, so it's the inverse temperature, okay, which is, as far as units go, Kelvin minus 1 here. So you're going to find some sort of a negative slope that's coming down through here. And again, we can turn around and say that the slope is going to be the negative activation energy over R. All right, so in a case like this, let's go ahead and again give 2 points like we did in the last lecture. So we pick out 1 point and we find that its values are, okay, and it'll be 1.24 times 10 to the minus third, and that's inverse Kelvin. All right, and then we also have a negative 0.45. And then for the other point that we'll have, it will be 1.41 times 10 to the negative third Kelvin, or inverse Kelvin, I should say. And it'll be negative 4. All right, so what we're doing here, we graph this out, and then we're picking 2 points on the slope in order to solve for this, or 2 points on the regression line. Okay, so if I were to plot this out, I would say negative 4 minus a negative 0.45. Okay, so that came from the values right here. Those are my y values, the ln of k. And then I'm going to put that over the inverse temperature values. So this would be 1.41 minus 1.24 times 10 to the negative third inverse Kelvin. Right, so if you solve for that, then you will end up with the negative activation energy over R equals negative 2.09 times 10 to the 4th Kelvin. Now, I want to turn this into just activation energy. So in order to do that, what I would need to do then is move the R to the other side, and because this is negative, we'll also ditch the negative, meaning I want it to just be equal to activation energy, not negative activation energy. So I get rid of the negative over here, and I put 2.09 times 10 to the 4th, okay, times, and I need the constant, so it would be 8.314 joules per Kelvin mole. Solve for that. And so the value that you'll get here, because the Kelvin will drop out, is that the energy of activation is going to be 1.74 times 10 to the 5th joules per mole. Okay, and if we wanted that in kilojoules per mole, we could obviously just rewrite that as 1.74 times 10 to the 2nd kilojoules per mole. So there we go. We have graphically found the energy of activation as we've gone through and utilized that setup. So one of the things that we can also connect here is how does temperature change the rate constant? Because if you come up and you look here, we've got the ln of a rate constant. A constant is usually considered something that doesn't change, but we're obviously graphing it with various points, so it's changing its value, and it's changing its value relative to temperature. So if you remember back when we talk about equilibrium, equilibrium constants can change based on temperature. It's the same thing here. The rate constant will certainly be temperature dependent, and as you manipulate temperature, you can increase frequencies of collisions and lower activation energy and things of that nature. All right. So what we want to take a look at here is how does the rate constant change with temperature, and that is given by the following. We can say that the ln of rate constant 1 compared to rate constant 2 is going to be equal to the activation energy over R times temperature 1 minus temperature 2 over the product of temperature 1 times temperature 2. Okay, so what this allows us to do when we have an equation like this is we can say, here's a rate constant for a reaction at a specific temperature. If I change the temperature to this new temperature, what would the rate constant become? So you can predict how the rate constant is going to change when you start changing the temperature. All right? So let's consider a reaction where we have a rate constant equal to 4.68 times 10 to the minus 2 per second. All right, and this will be the rate constant at 25 degrees Celsius, so 298 Kelvin. And we got to keep our K's here. This is big K for Kelvin, that's small k for a rate constant. Okay, so then the question can be, what will be the rate constant for this reaction if I increase the temperature and I bring it to 375 degrees Kelvin? Okay, so the way that we can do this, it's going to be a bit of a jumbled mess with everything we have to fit in there, but we utilize this reaction rate here, right? And we're going to solve for what will be K2, right? We have to find the second, so we could call this as K1, and this is K2, and this would be temperature 1, and this will be temperature 2 here. All right, so setting this up, what is it going to look like? Well, it's going to be the natural logarithm of 4.68 times 10 to the minus 2 per second over rate constant 2, which is what we'd like to find. And we can set that equal to, right, now the energy of activation, I should have laid that out, okay? The problem states that the energy of activation is going to be 33.1 times 10 to the 3rd joules per mole. Okay, so that's the energy of activation. We would need that in order to solve this. And so what we'll do is we'll put in 33.1 times 10 to the third joules per mole over 8.314, and that's the constant, so that's going to be joules Kelvin per mole. All right, multiply, and now you have to do the whole entire temperature portion. So this is going to be times 298 minus 375 Kelvin over the product of the two, so 298 Kelvin times 375 Kelvin. So you would have to put all of this in and solve for it. So let's start by finding out what this would be equal to, okay? And if you range it so that you just have your value here, you're going to find that it is equal to, okay, negative 2.74. So what I need to do then is I am going to take e to the negative 2.74, and that is going to equal 0.0646. Okay. Now keep in mind that this value is still going to be for 1 over K2, so I'm going to need to work with the inverse of that value. And if I do that, I'll end up with K2. And K2 is going to be equal to 0.724 per second. Okay, so this would be the new rate constant at 375 Kelvin. All right, and that will bring this lecture to a close. So that is the last thing we are going to talk about with energy of activation there. So if this was a helpful video, please remember to leave a thumbs up and smash the like button for the YouTube algorithm so it promotes our channel and we can create more high quality content. Head on over to chemcomplete.com. You can support us there. We've got lots of free resources. We have guides available for purchase, and I do offer one-on-one mentorship and tutoring if that is something that you need for part of your chemistry course that you're struggling through. So other than that, remember to hit subscribe so you're up to date with all the latest information, and if you leave a comment, I will do my best to get back to you as soon as possible. Thank you very much for learning with us, because there's a lot of different channels and choices, so just learning with us is a great way to support the channel, and I will see everybody for the next lecture.